Today we'd like to welcome Professor Florian Luca of Wits University, who will be presenting with us. Professor Luca is a Romanian mathematician who specializes in number theory with emphasis on Diophantine equations, linear recurrences, and the distribution of values of arithmetic functions. He's made notable contributions to the proof that irrational automatic numbers are transcendental and the proof of the conjecture of Erdős on the intersection of the Euler-Totient function and the sum of divisors function. Professor Luca received his Ph.D. in mathematics from the University of Alaska and has held various appointments at Syracuse University, Bielefeld University, the Czech Academy of Sciences, and the National Autonomous University of Mexico. He's currently a research professor at the University of the Witwatersrand. He's co-authored over 500 papers in mathematics with more than 200 co-authors and is a recipient of the 2005 Guggenheim Fellowship for Natural Sciences, Latin America and Caribbean. Prof. Luca is one of the editors-in-chief of Integers, the electronic journal of combinatorial number theory, and an editor of the Fibonacci Quarterly. And this morning, he's joining us to present a seminar titled On X-coordinates of Pell equations in various sequences. So please join me in welcoming Prof. Luca, and over to you, Prof. Thank you.
All right. Good morning, Diane. Thank you for the invitation and for the nice introduction. And I thank the Center of Excellence in Mathematics and Statistics for inviting me to give this seminar. So today I will tell you about X-coordinates of solutions of Pell equations in various sequences. And this is joint work with various colleagues and students, and you will see their faces as we go along. So let me start by saying, trying to explain what is this said in the title. What is a Pell equation? You start with a positive integer d, which is not a square, and you're searching for positive integers x and y with the property that the square of x minus d times the square of y is equal to plus or minus 1. You want d not to be a square because if d is a square, then the left-hand side factors into two linear factors in x and y. So you get a product of two integers equal plus minus 1, therefore each one of them is plus minus 1, and that doesn't have solutions. But it turns out that if d is not a square, then this equation always has solutions. And the way you do them, you have to find the minimal one, in the sense like the smallest x or the smallest y. And then what you do, you construct the element x1 plus the square root of dy1, which is an irrational number. You raise it to power n. You apply the binomial formula, so it becomes an integer plus root d times another integer. The integer, you call it x sub n, and the coefficient of root d, you call it y sub n. And it turns out that x sub n, y sub n is also a solution of that equation that you started with, the Pell equation. And there's a theorem saying that all the solutions are obtained in that way. So our equation always has solutions, and we know how to find them modulo finding the first one, which is related to continued fractions and other sides of mathematics. Now our problem, what is our problem about finding x-coordinates of Pell equations in various sequences? Well, take your favorite set of positive integers, let's call it U. And then let's ask the following question. What can I say about the square-free numbers d, or the d's which are not squares, such that your favorite set U contains a member of the sequence x sub n for sub n. So you take some d, you generate the sequence x n, y, n. For every d, you have a different sequence. And then you ask, what can I say about x-coordinates in those sequences, in my favorite sets of numbers? Unfortunately, if one formulates it in this way, the above problem is trivial. And what is the reason? Take the favorite number u. It could be a Fibonacci number or a square or whatever your favorite number is. You square it and you add 1 to it. It's an integer. You write it as a square-free integer times a square. And then you just kick those two sides, two numbers, one in this side and one in the other side, and you rewrite it as u square minus dv square equal -1. So in some sense, for every number u, there is some canonical Pell equation such that u sits as an x-coordinate into that Pell equation. And here I added one, but you can also subtract one and play the same game, switch around those two. So this first attempt somehow failed in the sense that the problem is trivial if you ask it in that way. So let's make it more interesting. We mathematicians, if something is trivial, then you can repeat it. So let's repeat it. What can we say about numbers D such that X sub n is a member of your favorite set U for at least two different values of n? That is, now I'm looking for square free integers D. I generate the sequence of x, y solutions to the Pell equation x squared minus dy squared equal plus minus 1. And as I go along the x's, I'm trying to find at least two of my favorite numbers. And I ask, is that possible? And what do I get? And it turns out that now the problem becomes actually interesting. So let's take you the first example. Most of this talk is going to be examples. I will give some ideas of some proofs at some point, but not in much detail. Take U to be the base 10 repdigits. What is a repdigit? It's a number that if you write it in the base 10, it only looks like a string of the same repeated digit. For example, 11, 222, 8,888, all these things are repeated digits. To encode that, you have a digit A, which repeats itself m times. The digit is between 1 and 9, so this number is equal to A multiplied by the number 11111 repeated m times, and that number is 10 to the m minus 1 plus 10 to the m minus 2 all the way plus down to 1, and you sum up this geometric progression and you get this element. Now, here's a theorem that I proved with Apollinaire and with Alain Togbe. Apollinaire is a student from Benin. This was done in 2016. Our theorem says, let x n y n be the nth solution of this Diophantine equation, x squared minus dy squared equal plus 1. Then this equation has at most one solution n, except if d is equal to 2, for which the first and the third solutions are there, and d is equal to 3, for which the first and the second x coordinates are there. To give some content to this, let me show you this calculation. Actually, this is how we got to the problem. Most people formulate a conjecture and then prove some theorem. What I do, I find an interesting numerical example, and then I prove a theorem that says that that numerical example is somehow the only one of his kind. So look at this interesting example. You start with a rep digit 99, and you square it, and you subtract 1. And you do it what you do in school. You say the difference of two squares is equal to the difference of the numbers times the sum of the numbers. The difference of the numbers is 98, which is 2 times 49, and 49 is a perfect square. And 99 plus 1 is 100, which is another perfect square. We'll put all the perfect squares together multiplicatively. So this thing just looks like 2 times the square. So now if I move this 2 times the square here, what do I get? I get x squared minus 2 times the square equal to 1. And where x is equal to 99. So this is a valid candidate, a rep digit, and it's certainly not the smallest one, because 3 squared minus 2 times 2 squared is also equal to 1. So actually that one is the smallest one. The smallest solution is the one that has x equal to 3 and y equal to 2. And it turns out that this one comes from taking 3 plus 2 root 2, raising it to power 3, and then you separate the x and the y, and the x becomes 99. All right, so here is Apollinaire. He was a student of Alain Togbe, which is the other person that has appeared in the statement of my theorem, and we will see his picture at some point as well. Now, let's go to another example. We can take U to be the sequence of Fibonacci numbers. The Fibonacci numbers is a sequence that starts with the values 1, 1, and then every value is the sum of the two preceding ones. So f1 equal 1, f2 equal 1, then f3 is going to be 1 plus 1, which is 2. Then f4 is going to be 2 plus 1, which is 3, and then you get 2 plus 3, 5, and you keep on going. Now, here is a theorem that I proved with Alain Togbe in 2016. We were wondering, what about if I put Fibonacci numbers for the x's in here? And we proved that this equation has at most one solution. Except in some small case. For example, when d is equal to 2, what happens is that the Fibonacci sequence repeats itself there. So for example, the value 1 appears twice. And the value 1 participates in this equation because when d is equal to 2, because you have 1 square minus 2 times 1 square is equal to negative 1. So that is a valid solution. And also, if you go to the third one, for example, 3 square minus 2 times 2 square is equal to plus 1, and 3 is a member of the Fibonacci sequence. It's the fourth one. So for d is equal to 2, there are some examples, but other than that, there's no example. How can you reformulate this result? You can get rid of this d and reformulate the result in the following way. You can say, let's look at this Diophantine equation. F sub n squared plus minus 1, f sub m squared plus minus 1 equal a square. There are some trivial solutions in here. For example, if the sign is negative and f sub n is equal to the first Fibonacci number or the second, which are 1, then the left-hand side is 0, which counts as a square. Then there is another diagonal case, namely n is equal to m and the signs are the same, and then this left-hand side is also a square. But let's consider the non-trivial cases. By a non-trivial case, I mean the left-hand side is not 0, and the signs are not the same, and the Fibonacci numbers are not equal. And the question is, can you find two distinct Fibonacci numbers such that if you multiply those quantities, you get a square? And the answer is yes. And I guess it comes from 1 squared plus 1 times, what is it, 3 squared plus 1? Oh, there is, well, anyway, there is some example in there which works for nm equal to 1 and 4. So for example, if this one is 3, then you get 3 squared minus 1, I guess that's 8. And then 1 squared plus 1, I guess that's 2. 2 times 8 equals 16. So that is the only non-trivial solution. And of course, this is a consequence of that, because if a product of two numbers is a square, it means that each one of them is d times the square for the same d by the fundamental theorem of arithmetic. So you're dealing with two solutions of this equation. Variations, repdigits in an arbitrary base. You can take the game that I played with base 10, you can play it with an arbitrary base. Take a arbitrary base g greater or equal to 2 to be an integer. You represent integers in base g in a greedy way as best as you can. You subtract the largest power of g multiplied with some number between 1 and g minus 1 out of your number n, and then with the rest you keep on going. You obtain the representation of a number in base g like you do in base 10. The repdigits are the ones such that when you write them in base g, they have the same repeated digits, so they look like this. And then these members of this set I'll call base G repdigits. And the theorem that I proved with my Ph.D. student Bernadette Faye in 2016 is that whatever we did for the repdigits works for repdigits in base G. Namely, if you have two x's which are repdigits for the same d, then that d is bounded in terms of g. And this bound is pretty bad. It's the exponential of 10g to the 10 to the 5th. So in some sense, it's an uncomputable bound. You cannot make computations using that bound. You have to have, you can make computations using an exponential bound. Let's say, if you have a problem in Diophantine equations and you have some answer saying, oh, d is less than 10 to the 100, then that you can do a computation. But if you have 10 to the 10 to the 100, then you cannot do a computation. But there are other ways to go around it. Now, this is Mrs. Faye, maybe attending some summer school or conference. She was a WITS, she's a WITS graduate. She graduated from WITS with a Ph.D. in 2017. And now she's a professor at the Saint Louis University, in Université Gaston Berger in the city of Saint Louis, which is a city in the north of Senegal, close to the border with Mauritania. Variations with Fibonacci numbers. Oh, you can do other variations. You can replace the plus minus 1 by the plus minus 4, and then you get the same idea that this equation has at most one solution n if you assume that you're working only with large Fibonacci numbers, which are at least 3. If you allow also 1 and 2, of course, you get a few other solutions for small d. And this is joint work with Alain Togbe, which appeared before, and Bir Kafle. Bir Kafle is a mathematician at the Purdue University, the Northwestern campus. He comes originally from Nepal. Proofs. Let me give you some ideas of how the proofs go. The proofs, at the beginning, they were quite complicated. They were a collection of tricks. For example, we take the nth solution to this equation, and suppose that I'm doing just the Fibonacci case. It turns out that this members of X coordinates of the Pell equation, they satisfy various relations among themselves. And that is not surprising, because if you think about it, the nth solution is obtained by raising some element to power n, which means that the m plus n solution is obtained by raising that element to power m plus n. But then you can first raise it to power m, and then you can raise it to power n, and then you can multiply those answers, and you still get the power m plus n. So because of this, if you rewrite those things, you get identities among them. Here is an identity. The nth coordinate can be expressed as a quadratic polynomial in terms of the coordinate at level n over 2, assuming that n over 2 is an integer. So meaning if n is even, then x sub n has this formula. So suppose that x sub n is a Fibonacci number. This means that I have to find Fibonacci numbers which are, suppose that it's a Fibonacci number for some even index. This means that I have to find Fibonacci numbers which are representable by this polynomial. Namely, there is that Fibonacci number is of the form 2x squared minus 1 for some integer. Now, there is a sequence that's called the Luca companion of the Fibonacci sequence, which has the same recurrence formula. Instead of starting with 1, 1, it starts with 1 and 3. And it turns out that that sequence, together with the Fibonacci sequence, they satisfy some Pell-type equation. So the Luca sequence square minus 5 times the Fibonacci sequence square equal plus minus 4 in the same index. So if you go to this formula, this means that for the Fibonacci, now you can forget about the Luca number. What you can think about is that for every Fibonacci number, if I square it and I multiply it by 5 and add or subtract 4 out of it according to the parity of the index, then I always get a square. That's a property of the Fibonacci number. So if in addition f sub m is 2x squared minus 1, this means that this equation here, which is a quadratic relation between Luca and Fibonacci number, transforms into this one. So I have an integer solution to y squared equal 5 times 2x squared minus 1, everything squared plus minus 4. The polynomial in here on the right, it's a polynomial of degree 4, which has four simple roots. And there's a theorem of Siegel that says that if you have an equation of the form y squared equal f of x, where f is a polynomial which has at least 3 simple roots, then this equation has only finitely many solutions in integers. And there's programs like magma and so on. These things are called elliptic curves if the polynomial has degree exactly 3. So there's programs which like magma, Kant, Cache, and so on, which what they do, they basically, you feed them some elliptic curves with reasonably small coefficients, and it finds all the integer points on it. So we go to that program and we ask, what about this equation? And it tells us that there's a few solutions, x, and using x you can find d, and then you figure out if that is convenient or not. Now, suppose that you have noticed that here I only used one value. I used the fact, but I used the extra information that the index is even. So suppose now that I have 2 values and both indices are odd. And I have 2 relations. If you have 2 equations, you can do what you did in school. What do you do in school if you have 2 equations? You learn that you can add them, or you can multiply them, or you can take linear combinations of them. You do whatever you can to obtain from those 2 equations a simpler equation. And maybe that simpler equation is going to help you. So this is what we do here. But our operation is very strange. We don't add them or multiply them. We GCD them, which sounds like a funny operation to do. But the GCD makes sense in the Fibonacci world, because the GCD of 2 Fibonacci numbers is the Fibonacci number of the GCD of the indices. I bet you didn't know that, did you? So this is a fantastic property. And when you go to the X-coordinates of Pell equations, they almost have the same property. This property fails if one of the coordinates is even. But if the coordinates are both odd, the GCD of 2 of these x's is the same as the GCD of the x in the GCD of them. I can also rescale them. I can rescale my Pell equation in the sense that if I have two solutions, x sub n and x sub m, with n dividing m, I can say that x sub n is the first one and the x sub m is the m over nth one, which sounds strange, but think about it. They come from raising something to the nth power. So if you raise something to the nth power and then you raise something, the same something to the mth power, and n divides m, then you can first raise it to the nth power and then you raise it to the quotient m over n. This is the explanation of what goes in here. So now my problem is a bit simpler in the sense that, oh, the first coordinate is a Fibonacci number, the nth coordinate is also a Fibonacci number, also this index divides that index. So we have some properties here. It seems like we start with nothing, but then we gain some property. Now, you use some properties of the Fibonacci numbers. For example, you use the property that the Fibonacci number, it has a compact formula, which I didn't write down. It's a linear combination between the nth power of the golden section, which is 1 plus root 5 over 2, and its conjugate, which is 1 minus root 5 over 2. Now, 1 minus root 5 over 2 in absolute value is smaller than 1. So the Fibonacci sequence looks like this golden section to power n multiplied by something, which is 1 over root 5. Plus something else, which is 1 minus root 5 over 2 to the n. But that thing goes to 0 at an exponential speed, just because 1 minus root 5 over 2 is smaller than 1 in absolute value. So in some sense, and here something similar happens. For example, this guy is smaller than 1 in absolute value, and this guy is bigger than 1. Remember, their product is equal to plus minus 1. That's how the Pell equation works. So usually this guy is huge, and this guy is tiny. It's 1 over the huge guy. So this means that alpha is huge. So alpha over 2 is close to golden section to power m1 divided by root 5. And the same alpha to power n over 2 is close to golden section to the power m1t divided by root 5. So somehow they shouldn't add up in some sense. So you write down these two relations. These relations basically come from the fact that when you look at Fibonacci numbers or X-coordinates of Pell equations, there is a chunk of it which is exponentially close to it, and then there is the other chunk which is exponentially small. So you write those two things. And then you say, well, maybe I should use them in some way. There's some way in which you can use it. Maybe you can raise this one to power t and try to eliminate that one or whatever. Here's what we decided to do. So we decided to do something else, which is again unorthodox. When I take these two relations, what I decided to do, so now I have xn and x1. Again, remember, I can do whatever I want with them. There are two equalities. I can add them. I can take linear combinations. I decided to divide them. Also, the division makes sense. The division, if you divide xn by x1, x1 is the divisor of xn always. And it turns out that xn over x1 is a polynomial of degree n in x1, which vanishes at 0. So x1 divides this polynomial. And it turns out that this polynomial further on, you can further reduce it. So after you look at the last term, which you say it's 0, you ask what is the previous term? So it's like taking the derivative and then making it equal to 0. It turns out that the previous coefficients is plus minus n. Well, in the Fibonacci world, something similar happens. F sub m1 divides f sub m1 of t. F sub m1 of t is a polynomial of degree t in f sub m1. But now it depends. It's one of two polynomials. There's a parity thing, and sometimes it changes sign, so it's better to square it. If you square it, it turns out that this guy is congruent to plus minus t squared modulo f sub m1. So these identities are true for every Pell equation and for every indices of Fibonacci numbers m1 and t. Now use the fact that in fact this guy is the same as that guy after you square it. This means that n squared is the same as plus minus t squared. So this means that f sub m1, which is x1, divides n squared plus minus t squared. So we obtained a fantastic property, namely that because f sub m1 is exponential in m1, and somehow it has to divide only the index, an amount that's about the index of the Pell equation. So now you combine, now this guy implies that guy. So for example, f sub m1, as I said, it's about the golden section to the power m1 divided by root 5, and this guy is at most, what it was, t smaller than n. This guy is at most 2n squared, so you recover that part in there. And then you use something called linear forms in logarithms. I'm not going to tell you what they are, but basically what it is, it says that if I have an inequality like this, what is important in here? It's important that I have some numbers which are bases, which are fixed, and I have some exponents which are variable. And this expression is very close to the number 1. So I have some sort of a monomial of the form alpha 1 to a power times alpha 2 to a power times alpha 3 to a power and so on. Alpha 1, alpha 2, alpha 3 and so on are known. The unknown things are the powers. There is an inequality called the Baker's method, which says that this expression is basically it's bigger than the exponential of minus some constant multiplied by the logarithm of the maximum of those guys, which is a fantastic thing. And now you compare it with this one, which is basically exponential in something which is linear in these exponents. Remember, here it was exponential in the log, here is exponential in linear. So then you get that m is at most logarithmic in itself, and it gives a bound on n. There is some ugly constants that you have to feed into here that are of the sizes about 10 to the 12. So once you actually compute them, it becomes n is at most 7 times 10 to the 14. And then, but then it's not so bad, because you see, even if this is 10 to the 14, this means that this guy, it's about 10 to the 28. Now you have to figure out what is the Fibonacci number, which is of size 10 to the 28. Well, I'm going to give it away. About the Fibonacci number, about every 5 steps, it acquires a 10. So if you go to about 5 times 28, which is about 140, then that's about how big your Fibonacci number can be. And this is what's written here. So if you are somebody asks you, what is the largest Fibonacci number which is less than 10 to the 100? Then you should say f sub 500. You're probably pretty close to the truth. Well, it is clear that this method also works for if you have plus minus 4 in here and so on. Then you get the repdigit case. It wouldn't seem like it would work in the same way, but it works in the same way. Why does it work in the same way? Well, suppose, first of all, that a is not 9, for example. Then I'm wondering, what about this equation, xn equal a 10 to the m minus 1 over 9. Then suppose that n is even, then I use again the fact that f sub n is this quadratic polynomial in x sub n over 2. And here what I can do with this m, I can look at it modulo 3. So I can say, oh, it's either a multiple of 3, or it's 1 mod 3, or it's 2 mod 3. So in some sense, 10 to the m is either a cube, or 10 times a cube, or 100 times a cube. So if I go in here, then I get a square equal something that looks like a cube. This is exactly the theorem of Siegel that I was telling you about. Siegel's theorem says that, well, if I put this 1 in the other side and divide by 2 and explicit what that cubic polynomial means, I need to check that it has distinct roots, then it will have only finitely many solutions. If a is equal to 9, it doesn't work, because this 9 simplifies with this 9, this negative 1 later simplifies with this negative 1, and then you get nothing. So this is the case when Siegel's theorem doesn't work, because you don't have a polynomial which has distinct roots. You have some multiple of a cube, which is a polynomial which has just one cube of one root of multiplicity 3. But anyway, so at least for a between 1 and 8 is worth. Then you can also do the GCD trick. And then you can say, well, fine, you convinced me about the GCD of the Fibonacci numbers and the X, but what about the GCD of 2 repdigits? Well, here is something, if there is something you want to take home, aside from guessing the number of digits of the nth Fibonacci number. As I said, you can just divide n by 5, and that's about the number of digits. Then another thing that you can take home is the fact that the GCD of 2 repdigits, so the GCD between 2 to 2 and let's say 8, 8, 8, 8, 8, 8, 8, 8, then it's basically almost the GCD of them. It's also a repdigit, except that you have to lie a little bit. So you have to lie and you have to pretend that 21 and 63 are digits. If you make this lie, then everything works. Here is, for example, the GCD between this 6 3s and this, I don't even know what this is, 9 7s, is 2331, which looks strange, but it's actually 21 times 111. And the GCD between this sequence of 6 9s and this sequence of, I don't even know what they are, how many they are, 12 or 18 7s, it's 63 times the repdigit. And this is something elementary. You can prove it by yourself. Now that you know that it works, you can take your piece of paper and you can make that calculation. So the point is that up to some minor modifications, everything works out. So then you have an analytic argument, and then you have a similar arithmetic argument, then you put them together. And of course, once you discover a few things and write a few papers, you feel very good about yourself. But then I said, let's try something for which this method doesn't work. So let's try Fibonacci numbers. Fibonacci numbers, they start with 1, 1, and 2, and then each member is the sum of the previous 3 guys. So the next member is 1 plus 1 plus 2, which is 4. The next member is 1 plus 2 plus 4, which is 7, and keeps on going like that. So we did the same problem, but now we looked at values in the Fibonacci sequence. And we got that it has at most 1 solution except for these cases. Now, this is the team. This is the alpha team. This is Amanda, Laszlo, Florian, and Alain. And I would let you guess in which order they are. And this is our research environment. This is how we were looking for Fibonacci numbers. Okay, so the problem is different from the previous ones because, first of all, remember in the previous case, I was breaking it into an even and n odd. First of all, we have no idea how to solve Fibonacci number is equal to x squared minus 1. Nobody knows how to do that. There's a general theorem that says that this equation has finitely many solutions, but nobody knows how to compute that. Secondly, we have no idea how to relate GCD of 2 Fibonacci numbers back to a member of the Fibonacci sequence, which are important ingredients. So what you do, you go back to your idea and you write down this equation x sub m equal. Let's go back to the Fibonacci numbers. This is the x sub n and this is the mth Fibonacci numbers. And I said it has, in each side you have a big part, alpha to the n, and here you have gamma to the m, and you have an exponentially small part. So what you do when you have exponentially big parts and exponentially small parts, you can divide things against each other. So instead of saying that 2 quantities are close to each other, you say that their ratio is close to 1. Now their ratio becomes alpha to the n, gamma to the negative m, multiplied by root 5 over 2. And you say that that is close to 1. Saying that something is close to 1 means that the logarithm of that is close to 0. You take the logarithm of the big part, let's say. And it becomes something that looks like this. It becomes n log alpha comes from here, n log gamma comes from there, and then maybe you have plus, maybe that's backwards. I think it should be plus root 5 over 2, just because this 2 sits down, not up with respect to alpha. So there's a typo in here. So anyway, and this one is tiny. Because if e to the x minus 1 is very small, then x is again as small as e to the x minus 1 was, because this means that x was very close to 0. So e to the x minus 1 and x are close to each other. Now what you do in here, if you know the number alpha, you use these linear forms in logs that I alluded to, and then this expression in here becomes bigger than the exponential of minus a constant times the log of the max of these 2 guys, whereas here is exponential of minus a constant and linear in the max, and that gives you a bound. But we don't know alpha. So then what you should do what you did in school. Please think of this big O as being 0. Then this becomes an equation. So then you write another equation, because you have 2 equations. Now this big O becomes 0. Well, if I have 2 equations which have a 0 in the right-hand side, and they are linear, then I know how to solve them. I just multiply the first one by something, the second one by something else, and I add them in such a way as to eliminate some unpleasant unknown. Well, but the same thing I can do here. I can take this one multiplied by n, which was on the previous side, take this one multiplied by n prime, eliminate the nasty unknown alpha, because this one I don't know what it is. It comes from the d which is not known. And then I get something. Here I know everything. Gamma is 1 plus root 5 over 2. I know this guy. I have to check that this is non-zero. These 2 guys are linearly independent over q. So if they were 0, then both n prime equal to n. So this coefficient should be 0, and this coefficient should be 0. But if that is the case, then mn equal m prime n prime. So they come from the same solution, which is not convenient. So now I just do linear forms in logarithm. Now this idea was very fruitful. So I'm going to start going a little bit more fast now. For example, we can even put sums of 2 Fibonacci numbers in there. And then we get that x squared minus dy squared equal plus minus 1. The only d's with the property that there are at least two x coordinates which are sums of two Fibonacci numbers are the d's in the set 2, 3, 5, 11, 30. Is it true that for every k greater or equal to 3, there are only finitely many d's with the property that x sub n belongs to kf has more than one solution n? Here we don't know. The point is, well, you can start in the same way, but there is unpleasantries along the way. You have to prove that certain things don't vanish and so on. And if you have too many of those guys, you lose track of them. If we replace kf by having at most k1s in their binary expansion, then the answer is no. So for example, I can cook up Pell equations with the property that the third solution and the fifth solution and the seventh solution, they all have at most 100 bits when I write them in base 2. So they have at most 100 ones and they have a bunch of zeros. So in that sense, so if it doesn't work for powers of 2, maybe it works for Fibonacci numbers, but we don't know. This is the colleague in this paper. His name is Carlos Alexis Gomez Ruiz, who was my PhD student at the Universidad del Valle, which is a university in Cali, Colombia, and he's a professor there now. We can do it with products of two Fibonacci numbers. That's the same alpha team that I showed you there with goggles. You can do it with products of two Fibonacci numbers, and the only cases are when d is equal to 2, 3, 5, you have at least two of them, but otherwise you have at most one of them. You can even do it with generalized k Fibonacci numbers. There are various ways of generalizing Fibonacci numbers. One of the ways is to look at generalize the length. So to say, well, let's say that every member is the sum of k previous members. And you say, fine, let's do that. But now you have to tell me the k initial values. Who are they? So people decided to work with k minus 1 zeros followed by a 1. And you arrange them in such a way that that 1 that is there is the first member of your sequence. That makes all the zeros live in the past. So in particular, the Fibonacci sequence, although I told you that it starts with 1, 1, 2, and then it actually is this one, because if you go in the past, you have 0 and 0. So this is a natural generalization. People looked at them. And look at this complicated slide. It says that if I have two members of the kth generalized Fibonacci sequence, which are both x coordinates of the same Pell equation, then they are either 1 and 2 or they are 1 and 3. And then there is some other values for those parameters. Now, this is how did we come up with that? Actually, you can there is some parametric ways you can express those generalized Fibonacci numbers for a while. At some point, you lose track of them. They become complicated. You have to use some Binet formula and so on. But for a while, they have clean formulas. For example, if n is between 2 and k plus 1 is a power of 2, then in the next slice, in the next chunk of length k, it's 2 to the n minus 2 minus n minus k times 2 to the n minus k minus 3. So well, look what I wrote here, 2x squared minus 1 and 4x cubed minus 3x. This one is the x up to. That's the second x coordinate in terms of the first. And this one is the third x coordinate in terms of the first. This one is also familiar from xn equal to x sub n over 2 squared minus 1 by now. So what could happen? It could happen that this is x, and one of those guys, it's either 2x squared minus 1 or 4x cubed minus 3x. And it's not so hard that that could happen. For example, you would say, okay, I'm looking for an expression like this. I want n minus k minus 3 to be equal to 0, and maybe n minus k to be equal to 1, or n minus k to be equal to 2, and then n minus k, if it's equal to 2, then n minus k minus 3 becomes negative 1. So this 2 cancels that 2. So this is how I get this negative 1 in here. And then I also want that n minus 2 to the n minus 2 is 2x squared, which makes n to be odd and gives x a certain value. And then you also know k and so on. And then you can play the same game there. And then you get some parametric families. And we prove that these ones are the only ones. This is a paper I wrote with my PhD student, Ddamulira. He was a co-student with Robert Tichy from the Technical University Graz in Austria. He graduated last year in April of 2020. And this paper, this result appeared in Journal of Number Theory. You can also do it with factorials. You can ask, what can I say about x-coordinates of Pell equations which are factorials? And we prove that they have to be just the first coordinate. And this is joint work with my PhD student, Mark Sias, which is rushing now to finish up his thesis before the 23rd of April and turn it into the graduate school. And this is Szalay and A. That's a picture taken maybe in December 2018 when Shanta visited us at WITS. This is in my office. Okay, now that's a complicated slide about Luca sequences. You take co-prime integers, r squared plus 4s different than 0. You create this quadratic equation. The fact that r squared plus 4s shouldn't be 0 is to make sure that these roots are not repeated roots. You also assume for some reasons that rs is not 1 minus 1 minus 1 minus 1. So you don't want x squared plus x plus 1, x squared minus x plus 1. These ones give you roots of unity. We don't like roots of unity here. So you can take alpha and beta with those roots and you construct un and vn according to these formulas. These are generalizations for the Fibonacci numbers, Luca numbers, and so on. And then what I proved with Prof. Stanica, which is a Romanian mathematician who works at the Naval Postgraduate School. He came at WITS many times. We proved that if you take a bunch of Fibonacci numbers and you multiply them together, and you want that to equal a bunch of factorials multiplied together, then the largest solution is this one. You have to make some choices about equal cases, because if you allow equality both in the left and in the right, then there is nothing stopping you from taking the solution, squaring it, and getting another solution if you allow equality. So you have to allow inequality somewhere. And we don't allow inequality here. We don't allow equality in the left. We do allow equality in the right. And this one is the largest solution. But then what we were thinking about, well, what can we say about these values of these Luca sequences, which are factorials? If the Luca sequence is known, for example, U sub n is known, being a product of factorial is easy. There is a theorem, a well-known theorem by Bilou, Anho, and Voutier, which says that if you have a member of this Luca sequence, like the Fibonacci numbers, if n is at least 30, 31, if n is bigger than 30, then the nth member of that sequence has a prime factor which is congruent to plus minus 1 mod n. In particular, it's at least as large as n minus 1. This is also true for the Fibonacci numbers in particular. The nth Fibonacci number is divisible by a prime factor that's at least n minus 1. That's true for all n greater or equal to 13 for the Fibonacci case. So in particular, if this guy has a prime factor which is of size n, then one of the factorials has to see this prime. So in this side, I have like a factorial which is at least of size n factorial, or n minus 1 factorial, and by Stirling's formula, that's about n over e to the power n. So this side now increases faster than exponentially, but that side is like the Fibonacci sequence, at most exponentially n, and you get a contradiction. But you get a contradiction if you know what the root is, because you need this constant. What I suggested to Mark to say, let's take any Luca sequence, and let's prove that if the nth member is a factorial or a product of factorial, then n has to be bounded unconditionally and absolutely. It shouldn't depend on the particular Luca sequence. And we bounded it by 62,000. And in addition, if the roots are real, then n is at most 12. That's a long paper which appeared in Monat's Hefte für Mathematik last year. And it uses properties of Luca sequences, sieves, results, very explicit results about prime number in arithmetic progression of small moduli due to these 4 people, Mike Bennett, Greg Martin, Kevin O'Brien, and Regnitzer, which is like a 100-page paper appeared in MathCom. Okay, now the last thing that I want to show you in maybe the last couple of minutes is this paper. Let's make a full circle back and go back to the paper with Apollinaire. And this is the math reviews of that paper with Apollinaire. And the reviewer liked it, but it says the proof breaks the problem into several cases which require a wide range of techniques to analyze, including analysis, elliptic curves, linear forms in log, and they seem to be specific to the base 10 case. So generalizing to other bases would require a separate work of equal magnitude. So I asked my student, Faith Sodor, I said, well, let's fight back for this referee, this report, this review, and let's actually make the problem manageable for every base. So this is the manageability of it. So this is basically the problem revisited that I did with Bernadette, where we proved that if you have two guys which are rep digits in base B, then the max of all these guys that you see in here, the N's and the M's and so on, it's bounded by this number, which, as I said, it's manageable. If you have 10 to the 100, it's manageable. So because of that, we took every base from 2 to 100 and simultaneously solved all these guys, and here is the D's. And here is my student, Faith. This paper has appeared in Research in Number Theory. Now he's working on another paper. He will probably graduate next year or in 2 years from now. And I'm not going to go through these details. All I'm going to say is that, for example, we have one issue there where, for example, you have some numbers, B, and you have some numbers, A1 and A2, which are smaller than B, and you have these three numbers, and life is easier if they are linearly independent over Q. And there are some cases in which they are obviously not. For example, if A1 equal to A2, or if 2A1 is B minus 1, because then this guy disappears, or if B is a power of 2, and so on. But then in our case, we had 788 triplets, for which they were linearly independent over Q, but they didn't fall into these categories. And here is some very strange of them. B equal B1 to the X. This guy is B1 to the Y C1. This guy is B1 to the Y2 C2, with C1 and C2 multiplicatively dependent. And here is what we got. Here's this very strange examples. And for these strange examples, some of them are not even defined over Q, but they are linearly dependent, multiplicatively dependent. So we had to go through this. So these problems, in addition from a theoretical part, it also has some computational part, which is highly non-trivial, and there's a lot of work to do there. And I'm going to skip over this slide. I'm going to mention that there is some similar work in progress on Y coordinates, but there the results is less satisfactory. For example, we have there the best you can do is to prove that there is no 3 in the sequence. 2, there is infinite families for which you can have. But so by 3, I mean, in general, given an interesting set U, then you can expect only 2 members of the Y coordinates to be inside the U. And if you ask for 3 members of the Y coordinates for the same D to be inside the U, then usually you get finitely many Ds. So, for example, if the set U is the set of numbers of the form 2 to the n minus 1, then the Y's can be of the form 2 to the n minus 1 for at most 2 M's. And this is best possible. For example, if you choose D to be of this form, then both the Y1 and Y3 are members of that sequence. So Y1 is 2 to the 1 minus 1, and Y3 is 2 to the something else minus 1. And that's it. I'm going to stop here.
Thank you very, very much, Florian, for a really comprehensive presentation. I know we're joined by sort of several mathematicians. The director of our center is present today, as well as a lot of our postgraduates. So a lot of our funded postgraduates have attended today. So I'd like to thank you and now take the opportunity to ask members of our audience to come forward with any questions, comments, or queries that they might have. Hi, Augustine.
Oh, yes. Yeah, nice talk. And the first time I saw the Lucas numbers, where you took the difference with the Fibonacci number, and given the fact that you had only 2 solutions to the equation you were discussing at that very point, I was wondering, did you use the fact that the Lucas number, the standard Lucas numbers, has only 2 squares in the entire sequence, that there are only 2 squares existing? Okay, that is my first question. And the second question is, now, okay, you apparently use only the standard Lucas numbers, okay, because the inception of Lucas is to kind of generalize the Fibonacci type sequences where you can start with any two numbers you choose and carry on and start getting sequences. I just want to know whether the results you obtained only adapt to the standard Luca number. No other starting pair of integers would give any reasonable result. Is that the case? Thank you.
Yes and no. So for example, the approach that I indicated at the beginning, using GCDs and so on, then that one uses the classical Luca sequence approach. Because what is important for that, of course, you can take a binary recurrent sequence. It has two roots, let's say alpha and beta. It will have a Binet formula. So its general formula would be a linear combination between the nth power of alpha and the nth power of beta, where alpha and beta are these two roots. Now with the Luca sequence, what happens is that they contain a zero at some point. So if the sequence contains the zero at some point, then the next value doesn't really matter what it is. You can assume that the next value is 1, because if it is not 1, it's some number, and that number is going to multiply all the rest anyway. So once you have a 0, then you can assume that the next one is the 1. And then it has this structure like alpha to the n minus beta to the n over alpha minus beta. This calculation, you can do it in your head. If you put n equals 0 in alpha to the n minus beta to the n, you get alpha to the 0 minus beta to the 0, which is 0. And if you put n equal 1 in your head in there, you get alpha minus beta over alpha minus beta, which is 1. So maybe I convinced you that this is what it is. Now, because of that, you can forget about the alpha and the betas. Let's go to x to the n minus 1. It has this cyclotomic structure now. Because it has cyclotomic structure, you can take GCDs and so on, and life is very easy. And then, of course, you say, what about if I start with two other sequences, with two other values? Well, it depends. I could start with the values 3 and 5. I still get the Fibonacci sequence. You see, I just started it a bit later. But if you start with 3 and 6 or something like that, then of course you get other coefficients for these roots. The cyclotomic structure gets destroyed, and then you don't have any one of those GCD properties and so on. So the approach that I indicated at the beginning is no longer going to work. But that approach that I indicated for the Fibonacci sequence, or more general, that one, it is going to work, because that one only uses the fact that the sequences you're looking at have one dominant root. If you have two dominant roots, two complex conjugate dominant roots, which are kind of finding each other, and sometimes they become negative, and sometimes their sum is small and so on, then there my approach is not going to work. So maybe I hope this answers your question. So I can work with more general ones, but there are also some restrictions about these roots having a dominant
root. Thank you very much, Augustine.
Sorry. What about the fact that you have that the standard Luca sequence, which you actually used, contains only two squares? Was it used in the proofs?
Maybe at some point it might be used. For example, if at some point I need to eliminate some small cases by searching for, let's say, integer points on certain elliptic curves, then this is exactly your question. Because then, remember I showed you that polynomial y squared equal 5 times Fibonacci squared plus minus 4, and I put Fibonacci to be 2x squared minus 1, and it became a polynomial of degree 4. Now, if I want the squares, then I'm going to get the polynomial becomes 5x squared, everything squared, so it becomes 5x to the 4 plus minus 4, and I'm looking for squares in there. So yes, so it depends. For example, maybe for some very elementary arguments, if we don't want to touch elliptic curves, we can say, oh, okay, we got to this value of the Luca sequence, which has to be a square, and we know that it's only these two values, and we can use that. But even if we don't know that, if it's some other quadratic polynomial, we can go to some computer and ask the computer what are the solutions, and the computer will tell us.
Nina from Stellenbosch, hi.
Hello, I just turned on my video. Hey, Florian, I haven't seen you in ages. You mentioned the paper of Binet and all, the very long paper. It's very computational paper.
Right.
And I think you referred to the 2018, and the funny thing, this is just a comment rather than a question, because that particular paper, funny enough, is, well, the last version is done on the 29th of November at 2:45 in the morning. So I don't know, is it the one that you used? But you didn't have, I don't think that paper is published yet. So, but I think those guys have codes somewhere that you could actually check that maybe those numbers are actually correct. Did you use?
Yeah, we used it in a very small range. We used it maybe up to about 1,000 or something like that. We didn't use very.
Oh, so it's you could check.
I'm sure it's fine. I'm sure the problems are maybe for larger moduli, but for our moduli, they were very easy. Not even 1,000, maybe 150 something.
Oh, something like that. So that's manageable.
You can reduce it to, for example, we were looking at the index n, right? So you can use the properties of the Pell equations and so on, and you can assume that the index n is a prime. And now if you look at the index n being a prime and you look at the pth coordinate of that, then you're going to get x1 sits in there, and then there's another polynomial of degree p minus 1. Since that polynomial of degree p minus 1 basically comes from the cyclotomic polynomial, it means that the prime factors in there have to be plus minus 1 mod p. And multiplicatively, it accounts for a big chunk of your number. Now, if you go to the factorial side, in the factorial side, the primes should be uniformly distributed mod p. So the primes p, which are plus minus 1 mod p, should not account for a huge chunk. And all the rest of the primes should account for a much smaller chunk. So if you put together this information, then you immediately get, even by a classical sieve, you get that p has to be at most a few hundred. And to rule out that, we used the paper of Bennett and those people. So we only use it in this range. So I think we are fine with what we've done. We use it extensively. Yeah.
Yeah. I think, because the paper is very complicated and involves heavy computations, but I think for small values, I think it's fine. No, but it's good to see you anyway, even if.
All right, thanks.
Excellent. Thank you so much, Nina. Luca, on behalf of the center, myself, and the audience, thank you very, very much again for presenting with us. It's wonderful to have someone from the number theory focus area presenting, someone who is so, widely published and notable. So a sincere thanks from all of us for presenting with us today.